Good morning, students. In the previous classes, we have studied about capacitor. What is the principle of capacitor? What is the principle? If an uncharged earth conductor is placed near to a charged conductor, then it can store a large quantity of charge. This arrangement, we are calling it as a capacitor. Now, how to construct a capacitor? Already I told you, you have to keep an uncharged conductor, which is earth, near to the charged conductor. Suppose there is positive charge on this conductor. If that is placed near to an uncharged conductor, negative charge is induced on it. On the other side, there is earthing. This is called capacitor. Now, how to construct a capacitor? So, while you are constructing the capacitor, there is no charge on the plates. See, you are keeping two plates together. One is earth. Arrangement is called capacitor. Now, what you have to do? You have to charge this capacitor. And the symbol for the capacitor is, this is a symbol for the capacitor. Parallel plate capacitor, symbol is this one. For cell, the symbol is like this. This is for cell and this is for capacitor. So once you construct the capacitor, there is no charge on the plates of the capacitor. Now what you will do? You connect these plates to a cell. Now what will happen? There will be charge flow towards the plates of the capacitor. And charge on the plates goes on increasing. As the positive charge increases, negative charge also increases. This process continues till the charge on the plates reaches the saturation value or maximum value. You know that work done is called energy. Now consider this case. In order to, initially, how much charge is there on the plate of the capacitor? It is 0. Now when you are connected to a cell or battery, the charge on the plates increases from 0 to Q. Suppose Q charge is there, plus Q charge is there on this plate, and here minus Q. So in order to increase the charge on the plates of the capacitor from 0 to Q coulomb, who is doing work? That is a question. Who is doing work? The cell or battery connected to the capacitor. The work done by the cell or battery to increase the charge on the plates from 0 to Q. You know work done is same as energy. Many times I told you. Whatever work you are doing for shifting the stone from the ground to the top of the building, that will be stored as the energy of the stone. Similarly, the work done by the cell to increase the charge on the plates of the capacitor from 0 coulomb to Q coulomb, that work done is stored as energy of the capacitor. Now energy, you know there are different forms of energy. Now the question is, what form of energy is there for a charged capacitor? You know, from plus charge to minus charge. What is there? There are electric field lines, right? Or electric field is existing. Similarly, between the plates of the capacitor, already we proved there is a uniform electric field, sigma by epsilon naught is existing. So the energy of the capacitor is existing in the form of electric field between the plates of the capacitor. So the form of energy of a charged capacitor is electric field. Now you have to find an expression for the energy of a charged capacitor. You consider a parallel plate capacitor. The charge on this plate is plus Q. Charge on the other one is minus Q. Area of each plate, that is A. Distance between the plates, that is D. You know V is equal to What is the definition of V? Electric potential, how we defined the previous class? The work done to bring unit positive charge from infinity to a point, or work upon charge. That is called potential. Or work done is equal. How can you write? V into Q. Is it right? Therefore, the small work done for increasing the charge on the plates by a small quantity dq. Small work done for increasing the charge on the plates of the capacitor by a small amount dq is given by dw is equal to v dq. Now you know C is equal to Q by V. So instead of V, you can write Q by C. So just substitute here. So you are getting dw is equal to Q by C dq. Now we need what is the total work done to increase the charge on the plates from 0 coulomb to Q coulomb. What is the total work done for increasing the charge on the plates of the capacitor from 0 to Q? That is actually called energy of the capacitor. You define energy of the capacitor this way. So total work is W, that you are getting by integrating dW. Now integrating dW means 1 by C integral Q dq. 1 upon C Q dq. Now what is the limit of the integration? It is very clear that charge is the variable. So initially how much charge is there? 0 charge. And final charge is Q. Q raised to 1. You know integration of x power n. What is the answer? Your answer is x power n plus 1 by n plus 1. So what is integration of q power 1? It is q power 1 plus 1. That means q square by 2. Upper limit q itself, lower limit is 0. So your answer is this one. So you can write it as half q square by C. That is energy of the capacitor. C. So this is the expression for energy of the capacitor. Half q square by C. Equation number 1. Now you can write some more expression based on the concept. Instead of q, you can write CV. See, C is equal to q by V. So instead of q, what you can write? CV. So this expression becomes half C square V square by C. Now C cancels. So you got the second expression for energy. What is that? Half CV square. If you want, you can make one more expression. Instead of this C, you have to write q by V. In equation number 1, half q square is there upon. Instead of C, you can write q by V. Now q cancel, V is going to the numerator. So your formula is half qV. So you got 3 expressions for energy of the capacitor. Which are the expressions? So energy is equal to half CV square is equal to half q square by C is equal to half qV. These are the 3 expressions for energy of the capacitor. The 3 expressions for the energy of the capacitors are half CV square, half q square by C and half qV. Now another term is there, that is called energy density of the capacitor. That is equal to energy upon volume in between the plates. How much volume is there in between the plates? That is equal to area into distance between the plates. See? These are the 2 plates and area is A, and if you multiply with the distance, you are getting volume in between the plates. So total energy divided by volume between the plates, that is called energy density of the capacitor. So therefore you can write energy density of the charged capacitor is equal to half CV square divided by area of the plate into distance between the plates. Now read this question. There is a parallel plate capacitor with area of each plate 90 centimeter square. Area of each plate A, and the distance between the plates 2.5 millimeter. Connected to 400 volt supply. So V is equal to 400 volt. So three values are given. Area of the plates 90 centimeter square, distance between the plates 2.5 millimeter, and V is equal to 400 volt. How much electrostatic energy is stored? So electrostatic energy stored in the capacitor, there are three formulas with you: half CV square, half Q square by C, and half QV. Which formula you can use? That's the question. Because only V is given, so you have to select either this one or this one. So you can find energy is equal to half CV square. And you know what is the formula for capacitance of a parallel plate capacitor? That is A epsilon naught by D. So you can write A epsilon naught by D into voltage square. Now replace the values. Half into area of each plate 90 centimeter square, and that is same as 90 into 10 power minus 4 meter square. Epsilon naught 8.85 for 10 power minus 12 by distance between the plates 2.5 millimeter. That is 2.5 into 10 power minus 3 multiplied with voltage. Voltage is 400, so it is 400 square. If you calculate this one, you will get your answer as 2.55 into 10 power minus 6 joules. So this is the energy stored in the capacitor. Now the second part. What is the relationship between energy density and electric field? So this energy density you have to connect with electric field. So energy density is equal to, second part, energy density is equal to energy upon volume in between the plates. So energy is half CV square by AD. Is it right? Now instead of C, what you write? C is A epsilon naught by D. So just substitute that here. Half into A epsilon naught by D into V square by AD. Is it right? Half C is A epsilon naught by D, V square AD. You know E is equal to dV by dr, negative, is actual relation. In the case of capacitor, this will become E is equal to V by D in magnitude. So instead of V square, you can write E square D square. V is equal to ED. E into D is equal to V. So your final answer will be half A epsilon by D into AD. Right? Now V square means E square D square. ED is called V. So V square means E square D square. Is it over? So what is the question? What is the relation between energy density and electric field? So now very clearly you can see D square cancels, area cancels. So your formula is half epsilon naught electric field square, and this is called the energy density of a charged capacitor. Energy density of charged capacitor.